Okay, everybody. So let's welcome our next presenter. So it's Matt Mycene, who is a senior evangelist on Linux and containers, and he's going to tell us about containing complexity with reproducible workloads. So, yours.
Thank you. Доброе полудне, мoj děkuji. That's all of my Czech. Thank you very much. Yeah, I have a big, long title, a senior evangelist, blah, blah, blah. It really means I talk to people about what they want to do with Linux, and then I show people what some interesting things that people are doing with Linux are. And we're going to talk about containing, that really should be 4 reproducible workloads, but details. So how many people in this room know what containers are? Good, we're in the container track. I'm in the right room. Probably most of what you've heard today on the internet, at DockerCon, at KubeCon, at Red Hat Summit, at FUDCon, wherever you go, you hear microservices, DevOps, CI/CD. These are all the things that most people talk about when they talk about container workloads. What goes inside a container? 3-tier applications, 12-factor authentications, 12 steps to CI/CD and massive scale with OpenShift, right? This is not what I want to talk about today. I want to go the other direction though. I want to talk about the batch job. And I don't mean the batch job from 1960s mainframe computing exactly. I'm talking about single run compute processes that do a thing on data and then exit. They could be massively parallel, but they're generally one-shot jobs and then repeated, deliver a single set of output, if that's some sort of data result, if that's a web page, whatever that is. And these are quite common sorts of jobs, right? Talking about things like financial reporting, quarterly jobs that have to be run to make sure that the books balance, to put some sort of audit trail in place, some sort of data analysis and modeling. Data science is huge right now. Lots of data science goes on, and we'll talk about how we can use containers to run some of these jobs. The same sides of bioinformatics, genomics, scientific computing in general. Petrophysics, oil and gas, we're starting to see a lot of these same sorts of jobs, right? Anything that does modeling, anything that takes data and spits it back out and generates pretty pictures like fluid dynamics, some of my old customers from the US Department of Energy. These all have the same sets of base problems that we talk about when we talk about containers for web apps, right? We've got library dependencies. We've got hardware dependencies. We've got sprawl within various different kinds of development environments to do these things, because primarily these things are written in Python or in R for the most part. And so, you know, how many people here write things in Python? How many people have run into positions where, you know, your virtual end works to a certain degree, but then you run into dependency issues within your virtual environment that you set up just to your dependency issues, right? With these sorts of environments, many people resort to virtual machines to contain all of the dependencies and make sure that they get a consistent environment. We've got some additional complexity with these sorts of workloads, mostly because of the class of computing and the results that they need. Environmentally, these can be very sensitive to changes in the environment. We want to make sure that our results are the same on the same set of data, no matter what. So minor differences in versions of libraries, differences in versions of interpreters could have massive issues with our reproducibility. The reproducibility in and of itself makes for a strong requirement that these things will run exactly the same and produce the same output. Works on my machine for a data scientist could burn at least a day, if not a week, simply trying to reproduce a result from an experiment they got from a colleague. We have portability requirements. We need to be able to run these jobs in multiple different environments, possibly run by different entities, right? We need to be able to take an experiment, built and run by, let's say, an observatory somewhere in the US, and then those results need to be shipped to Tokyo in order to be run against a similar set of data to see how the analysis works somewhere else. We want to make sure that those run exactly the same in both environments. Our users don't necessarily know all of the ins and outs of building virtual machines and building systems. They'll generally possibly know how to install packages via something like pip or for R for CRAN, but they're generally not going to be able to build a virtual machine, manage a virtual machine, which puts a lot of that on the developers, on operations to make those available. It can be difficult for them to enter a virtual machine in order to try to do their work. And one of the more interesting ones then is also peer review. There was a movement a few years ago for an idea called executable papers, so that when you published a paper and you published your data, you also published an executable version of your code. That way it could be reviewed and peer reviewed. The problem was all of these things about environmental changes and whatnot would affect whether or not that was reproducible. If we were instead shipping Docker containers with our code and perhaps a Docker container with a volume for our data, this would be much easier to do a peer review that carries along all of the necessary requirements. And reproducibility is important. There's a recent study done on a drug study that found that there were 53 published papers on new regimens in drug treatments for cancer. They went back through the original data, they went back through the original experiments and found that only 6 were actually reproducible from the published materials. Right? So we have 53 landmark studies that cannot be reproduced. This is a huge issue in many, many different environments for very, very different kinds of compute workloads that do some very critical things. In order to see how we can use containers to solve some of these problems, we're going to use a basic pattern to build our platforms and build our containers. And we're going to leverage the basic idea and the concept that we've got immutable layers that we know run over and over within our environment. Specifically today, I'm going to be talking about Docker and Docker build, but this is true for any of our container environments, right? If we're using Cryo, if we're using Rocket, the image format doesn't matter, the runtime engine doesn't matter. We're just using Docker today as the example. So first we're going to start with our base. Our base is generally upstream, vendor provided. Could be something that if you have an environment that needs very specific sorts of hardware enablement, maybe something that your operations team might put together. But this is where we're going to start with a very, very limited set of runtime environments, just enough to get off the ground. From there, we'll add what we're calling our platform. So our platform, this is where we start adding in most common required framework elements. So for, say, Python, this is where you'd add the things that are in most common use for your particular environment. And then from there, end users can then go ahead and use that container as their downstream for their application specific dependencies and also their code, right? Fairly common pattern. Anyone already using this for general web applications? No? Okay. Well, hopefully we've learned something then. So today we're going to talk about specifically some scientific computing for Python. And I'm going to build a certain number of containers, and we'll walk you through this and so what the Docker files look like. So commonly for a data scientist, right, we're going to start with RHEL because one, I have access to it, and two, I built this for another customer. Generally, there's two competing is a bad word, but there's two different options out there that are majorly used for linear algebra libraries. One called Atlas, one called OpenBlaz. This would be a complicated decision tree for a scientist to have to make in order to know how to select a linear algebra system within their code. So generally winds up being a place where different virtual machines would be made available to support the different linear algebra systems. They both use NumPy, they both use SciPy, which are very common Python mathematics libraries. We'll then add a layer for scikit-learn. Scikit-learn is a machine learning library within Python. It actually has some traction in data analysis and some other languages because of the way that they do matrix math and some other things. And then we'll go ahead and we'll drop a data analytics workload into that as an end user. Right, so we've got our vendor-provided platform. Right, this is where we'll install certain levels of required things. We'll go ahead and we'll build our internal platforms. We'll talk a little bit about inheritance and how we can layer these in order to provide different experiences for things. And then we'll go ahead and we'll talk about, and I'll show you how a end user might use these to do their daily work as well as do some production value work as well. Okay. So most of this is going to be a demo because it's not a particularly complicated story to explain, but hopefully we'll show you some value and we'll show you how this works. This is all in a GitHub repo. NZWolfen is how you find me on GitHub, and this is called Contained Science in my repo. So if you want any of the code, it's there. I am using. Anyone heard of Kaggle? No? One? Good. So Kaggle is a public data science competition environment. People publish various different sets of data that they want to have analyzed. They'll put competitions together, and it's also a place for folks who are doing data science to share ideas, to collaborate on various different environments. I'm using a Red Hat competition that closed in September of last year, and that was actually not intentional. I went to Kaggle looking for scripts that I could download for Python and for R, and it just happened to turn out that the two that I found that were Apache licensed that I could reuse and remix were Red Hat based. So this wasn't intentional on my part looking for Red Hat material. There's there's a set of data, and this has got training data, and we're trying to figure out some area under the curve sorts of analyses on behavior of people based on some training data and whatnot. All right, so let's switch over to a terminal, and we'll show you what some of these things look like live. If I can get the terminal over there. Why will you not come to the front? Okay. There we go. Of course. Sorry, I forgot to unpause the virtual machine. 1 second. Everyone can see that okay, or should I make it bigger? Bigger? I can do bigger. Okay. So this is the basic project. We'll go ahead into the Python directory and take a look at some of our Docker containers. So this was one of our base platform containers. So for this particular project, I just went ahead and we're using the RHEL 7 upstream directly, so I don't have anything fancy here. And what we're going to do for this particular user is we're going to go ahead and install these packages. Right, this is our NumPy, SciPy, and our Atlas that's just distributed as BLAS within the current Red Hat family. And we're also going to go ahead and make sure that everything that we need for pip works. So that way we have an easy way for our developers to go ahead and add additional libraries to their environment without having to worry about whether or not it's available or installing GCC and these sorts of things. We're just going to clean up after ourselves, and then we're going to go ahead and our Docker environment is going to just say that our entry point, which is what we're going to run, is the Python interpreter. And our command here, just to have something there, is going to be able to spit out the help command. So if I were to go ahead and run, it just spits out Python help, right? We'll go ahead and we'll talk a little bit about why we do that in a second. So our next layer was then to say that we're going to add the scikit-learn packages so that we can do a little more deep analysis on the data files that we're going to do later. So we're going to go ahead and this inherits everything that we've got in our Atlas container. Right, so we've got pip available based on our previous container. So we can go ahead and just say we're going to install pandas, we're going to install scikit-learn and XGBoost because they wanted to use some matrix math that's a little bit different than what's available in the machine learning kit. So we can, again, use common things that our data scientists or scientists may be aware of. Right? They know how to use pip in a virtual environment, but they don't have to learn Yum. They don't have to learn any of the operating system things that they would need to if they were working in a bare virtual machine environment or something along those lines. And just to make things simple, I've gone ahead and we're going to go ahead and say that the environment is the same. Since I'm not changing that entry point, we could just inherit that from upstream, from the Atlas environment. So we now have 2 layers of available platforms. And this is what our experimenter environment would look like. Right? So we've got a pair of basic test scripts we're going to run for Python. We've got those tarred up into a single experiment delivery file. And very simply, we're going to say from that scikit that we just built, we're going to go ahead and we're going to make our work directory /temp. We're going to go ahead and add our tarball, which we'll go ahead and expand that and make those available. And you'll notice this does not have any sort of entry point. We are going to use that straight from our scikit. So what that allows us to do then is to do things along the lines of, and this is all copy and paste, so you excuse me a second. I'm having trouble here. All right. So we know that we have Python installed on this particular system, right? But it helps if I hit the right things. This laptop, this virtual machine, does not have NumPy on it. Right? So this is not a suitable environment for anyone to do development work on. However, okay, this is not going smoothly. Right. Apologies, you were not supposed to watch me have to type all this. I was supposed to copy and paste all this stuff. But we can see within our Atlas particular container, we've got all of our NumPy configuration. We can see what's going on here for for what we've built and how we've built it. I've already gone ahead and built an oblast, which is the other alternative that we had for our linear algebra systems. So we've got now here, instead of where we had userlib64 Atlas, we're now using the lib openblaz installed by source, and I'll show you that in a second. So we've got options, and as far as the data scientists are concerned, they don't have to worry about switching back and forth between Atlas or openblaz in code. They can just select the right Docker container to start from when they build their experiment and go ahead and use the right libraries. So far this is all fairly standard. No big deal with Docker containers, very small Docker containers, and we're using things that are freely available within the standard sorts of RPM repos. And that's not very interesting, is it? So we'll take a look at openblaz. So openblaz is actually something that we're going to go ahead and compile from source, from upstream, and we're going to go ahead and take a look at how we might manage some of those Docker environment issues on how we would provide multiple versions of this to a user. So the first thing, again, this is just pulled straight from the RHEL 7 base. But the first thing I want you to notice are these three args up top. People familiar with the argument idea in a Docker file? 1, 2, okay, 3. So arguments are exactly what they sound like. It's a way for within a Docker file to pass things on throughout the rest of the Docker file without having to try to screw around with environment variables and getting those picked up. So these are all locally scoped to within the Docker file. We're going to go ahead and use those to set up some labels, so that way we can inspect the Docker file later and we know what version we've actually produced, because that's going to be important. We're also going to go ahead and use that in, since we're going to go ahead and build these actually straight from source. The other place we're going to use it is when we clone these from GitHub. We're going to go ahead and make sure that we check out the tag that we're looking for, right? And this is all, we're installing all the things we would normally need for to build this from source. GCC, Fortran, setup tools, all that kind of good stuff. Git gets installed here. And then we're going to go ahead and make sure that all these things get pulled from source. We get the right versions so that we can tie together the correct version of openblaz, the correct version of NumPy, and the correct version of SciPy. So that all of these things, as they get built together, will be useful, because that's always a big issue. And again, we have the exact same Python entry point that allows us to get that openblaz just runs that Python help file, or help command rather, as it works. So the other thing that the build arg allows us to do, and we'll go ahead back here, is normally that went much faster than I expected. These are all cached, so it's not going to actually do anything. So there was my Docker build, right? So normally you would build Docker, you throw it a -t. You can see that those variables show up as arguments, and that we grab and we clone the right version of all these things, and go ahead and build them. Now, it doesn't get exposed as to what they are on the output, so you have to be careful that you know what you're doing. The other thing, though, that we can do, since we have these, this keeps going back to a bad place. Since these are actually exposable from the command line as build arg here, we can go ahead and override those at build time within Docker. So if we set up our Docker file to take these sorts of arguments, we can simply pass the different variables we might need for different checkouts to provide different versions. The other thing that we need to be able to do and we need to be aware of is once we do that, we now have 2 different Docker containers with 2 different versions. This is where not just labels, but tags and tag maintenance would also be important. So I went ahead and I tagged that one as V109. Oops. So if I look at what images we have available, we've got a latest, we've got a V218, and the 219 that I just built. But you'll also notice that latest is not latest, right? I built this originally on the 2.18 stream without giving it a tag. Docker latest is always a convenience tag. So if we do want to go ahead and make sure that our latest corresponds to a particular version, we need to make sure that we remember how our Docker tags work and not to assume that Docker latest will always point to latest. So if someone's going to take a look at these and try to say, oh, well, it should be 219, why is this not working? If we went ahead and looked at the latest version, this is, it's going to go ahead and tell us that the label is, it's the 218 version. So we need to be careful when we actually start using versions and tags and these sorts of nifty tricks that we go ahead and we use the right things. So these tags are the ones that get set based on those build args. So this also gives us not just the ability to say, okay, our experimenters and our scientists can go ahead and take a look at the tags, but they can also use Docker inspect to try to figure out which actual versions will match, because those will be picked up from the build args and should be then correct based on the Docker file we built. All right. So we've gone through and we've taken a look at how we might go ahead and use these as inherited platforms. Some of the issues around labels and how we can use some of the build args to make our work easier to provide multiple different versions of tools and things available to our community. One of the other things, and I've got some of these pre-built, is that, that's not what I want to do. Apologies. We can also do things from alternate versions of base images, right? Rel 6 and Rel 7 are very similar. We've actually got distributions for NumPy, SciPy, and Blaz. But if we have people who are using older versions of software, we can go ahead and make those available on newer versions of hardware and operating systems, right? So if we have an existing set of experiments, existing set of various different reports that are all running on Rel 6, we don't have to worry about trying to completely migrate and rewrite those. We can just go ahead and containerize them, run them on a new environment, something that may have access to faster networks, different disk, more CPU capacity, or just a newer environment. And we can go ahead and we can isolate those changes to the experimental environment from the hardware layer. And that allows us to be able to reproduce older experiments and older results on newer systems. And just to show you that this stuff actually all works as advertised and as necessary, we'll go ahead and we'll play around with the R environment. So I mentioned that we have some actual benchmarks and tests that I put together from an upstream. And I'm actually using the R benchmarks. This is just a standard benchmark. I don't remember what I was about to say. We're going to use the R version because the Python version takes about 8.5 gigs and about 20 minutes to actually run the same analysis as R, which is one of the reasons that R is gaining popularity for data science over Python. So this is all just running through saying, yep, this is our base container, it all works. And this is just kind of a standard R benchmark that we use online to do various different kinds of things. So what I've got is a set of, this is the Python and R scripts. We've got 3 different sets of data. We've got a training set, we've got the actual test set that we want to work, we've got a secondary correlation that we're trying to get done. So we do have inputs and outputs. Okay, good, I'm glad that failed because I didn't want to do that. So what we're going to do is we're going to go ahead and run the Docker file, and we're going to go ahead and mount these input and output directories as volumes. We are running with SE Linux turned on, which is why we need the little -Z at the end of our stanza so that we make sure that Docker goes ahead and sets the right context on those 2 directories. And this will go ahead and just take those 2 directories, pull them into the running container that we built for the experiment, and go ahead and, okay, that's excellent. This is where it always breaks. This should not break. Uh-oh, I think I know what I did. Give me 1 second, sorry. All right. That's not in there. All right, so I apparently forgot to put my R script in my benchmark. All right. So we'll get a live demonstration, very live demonstration of how you might do this for an experiment. So we don't actually have the benchmark, the R script in there. All right, so let's skip ahead and we'll just do the Python work. It's never a real demo unless something goes absolutely wrong, so at least I feel good about that. Okay, so we've taken a look at how you might use these as a administrator, right? How we might provide environments to scientists, to data analysts, to various people who are attempting to have runtime environments that are consistent across multiple different kinds of platforms. Has anyone actually tried to develop inside of a container? Doesn't work very well, does it? So you lose, how do you actually get your running code in, test it, bug fix it, rerun it, those sorts of things when you're working with your code now inside of a container? Pardon? You can mount it as a volume. Right. And that's exactly how we're going to do this today. What we have here is the same environment. And because that's actually why we were going to go ahead and use those entry points straight into the Python interpreter. Typically, the way folks might go ahead and build a local environment, right, is just build a Python script, run Python against the script, and have it execute. With the way that we set up that entry point, we can go ahead and set up an alias or something along those lines to make things easier, like this one. So I've created a scikit-py alias, which just goes ahead and runs that Docker IT, and exactly as suggested, creates a volume out of the local current working directory, mounts it at temp. Right? Temp was our work directory. So anything that we run locally, we should be able then to run within this particular instantiation of the Docker file. Right, so this is the one that takes too long, which is not the one I wanted to run, but we'll go ahead and run it and I'll kill it. So you can see that it's going ahead and it's taking the test and training data, it's taking the correlation data from the individuals, and it's going ahead and it's figured out the various different shapes of the data, and is now doing various analysis to try to fit a nice curve to it to figure out what sorts of correlations we're trying to do. So this is one of the tricks you can use in order to provide this complex environment to a end user so that they can use exactly the same sorts of interpreters and libraries they would find in the runtime environment on their local environment without actually having to install anything. I was just in a talk, anyone saw Owen Taylor talk about Purple Egg? He's actually taking a slightly different tack to this exact same problem of how do I develop against containers from a local environment for things like Python and some other languages. And it's got some real interesting promise and does a lot of the underlying how do I build a container, how do I run local content inside of a container against a different environment. It's still in big development, so he's looking for people who have use cases, who have questions, who have various different things that they might want to contribute. So it's Purple Egg on GitHub is the name of the project, and this is actually running through and doing some things. All right. So that is I'm not going to go ahead and let that finish because that's going to take way too long. So this is a basic run through of some of the things you might be doing, but as you can see, there's a lot of manual things and there's obviously things that can go wrong. There are other things that we haven't talked about. A lot of these sorts of environments and a lot of these sorts of jobs are usually run in distributed systems. So these are the things that we're leaving for you guys. MPI works. I've seen MPI in a Docker container. It doesn't have any issues as far as runtime, but there are some issues about how do you get it actually up and running and masters and workers talking to each other and how do you get it coordinated. Schedulers for these sorts of jobs and how do we get the parallel processing. This could be something for Kube. This could be something for something that understands it like Moab or one of the more typical HPC environments. GPGPUs, FPGAs, this is very, very useful in these sorts of calculations. And within a Docker container, it's a lot easier than within a virtual machine. VMs introduce the need for PCI pass-through or emulation layers and makes GPGPUs sort of sticky to try to get to use well. CUDA toolkits are tied very tightly to hardware and to driver versions. But with a Docker container, knowing your environment, you could actually map some of that complexity. Possibly that would be why you would build your own base layer or platform. And you could then, you'd have to still run it privileged to get the device mapped in, but it's much easier to use a CUDA toolkit this way. There's a couple of different implementations that are floating around online that show you how to do these sorts of things. And then building, right? There were some interesting, possibly, tips that you hadn't seen on build args, but that's really not a scalable way of doing things, right? Manually hacking on Docker build files, it's not all that conducive to long-term support efforts. That said, there's a lot of different ways to go ahead and build containers. I've used it and generally tend to use Ansible for a lot of the things that I'm doing inside of a container. For me, it's easier to do things that way and to have things consistent that I can run as bare metal virtual machines or container targets. I'll use one set of content that just change the actual target you're looking at. But it's also possible that because we were looking at things like distributed processing, looking at things like how do you use continuous builds for both security and for experimenter updates, something like the OpenShift platform might be useful here. We get Kube for free, we get the build service for free. So looking at things like Origin and the OpenShift container platform and figuring out how we might provide some of these build services would be possibly a next step to make this a little more than just a laptop demo to get people thinking about how this might work. So with that, thank you very much. I appreciate the putting me up with issues with the live demo. And any questions? Here. What kind of performance impact do we get when we get inside of Docker? Well, let's go ahead and let's see if I'll get one of these things to run on purpose. So Docker overhead in and of itself is fairly light. The Docker really only comes into play in and of itself. Whoa, why is that? Sorry. It really only comes into play on startup and management. Once it's up and running, Docker doesn't really get in the way of the process. So generally, we find that process performance is pretty on par with bare metal, and and once you start getting into things like off host, right? That's where you can also start getting into some issues, like if you do run RHEL 6 on top of RHEL 7. What happens there when you drop it into, you've got brand new network drivers that the base layer may not know about. If you have things that are latency sensitive, and we're talking about communications, that's where it's possibly better to start using things like the dropping into the host network namespace rather than trying to worry about an overlay network. But that's going to be probably the single biggest impact that you'll have to take a look at when you do these sorts of workloads from a possible performance impact.
The other one would be probably concurrent running multiple Dockers on the same CPU, because the schedule would usually allocate your process particle CPU and not start fighting between multiple.
Sure. Yeah. So the question was not just from a performance latency or a network latency, but also things like scheduling impacts. So if you are doing things that are NUMA aware, that's another one where NUMA awareness is something that we would have to start looking at. If CPU pinning were something you wanted to look at, that might be possibly outside the range right now. I don't know if we can do that very well with C groups. Other questions? Mm-hmm. Yeah, so the question was, how do you deal with container management? Because yes, I was doing the very, very bad thing of just running containers. And if you take a look, there's probably 40 or 50 or 60 exited containers sitting on my machine right now. That's another one where having another layer above just Docker run is probably necessary for these sorts of things. That gets a little bit into the scheduling left to the reader exercise. Because because they exit and they exit cleanly every single time, we would have to look at something else. It could be Kube, it could be Docker Swarm, it could be Compose, it could be a lot of different things. But definitely, it's a good catch because that's demo purposes only. Go ahead. So the question is, reproducibility is nice, but is tying experiments to particular versions of maths libraries necessary? Or does it hurt reproducibility and performance? Is that a fair restate?
Not reproducibility, but validation. Like you can compute the result with a specific math library, and when a different math library says something else,
Sure.
what does it say about the experiment?
Sorry, so it was reproducibility and verification with different math libraries. So usually the difference between something like Atlas, OpenBlaz, LAPACK, or something along those lines, usually that's a layer higher at the library layer, that linear algebra should be linear algebra should be linear algebra. So that these two runs here between, say, the OpenBlaz experiment container and the scikit container, those should, those various different dot executions should just be faster because of the implementation. And if the math is in and of itself incorrect, then that's a bad library you shouldn't be using, and people in the community should already know about that. But, and yes, it might be a bad experiment. Yes, you could pull down a version of OpenBlaz from GitHub that has a bug in it, and yes, you could throw off your entire experiment. That, however, that could happen no matter if you're in a container or not a container. If you just happen to grab a linear algebra pack that isn't really generally considered useful by the community. Yes.
Are you also thinking putting IPython inside the framework?
So the question was, have I thought about, or other people thought about putting IPython in the framework? Yes. So Jupyter themselves actually have published their own version of various, and they use sort of the same base thing, right? They've a base notebook, and then they publish different kinds of notebooks with other things in them. As you can see, they're not small. Kaggle, the competition site that I talked about, does the same sort of thing. They produce these big, giant images of everything you might use in Python for any one of their competition, and they're open source. So if you find a new library, PR on GitHub, that's also like 5 gig. In fact, this isn't really just an issue with these guys. Oh, no, there we go. That's too much. The R platform, which all I'm doing is pulling stuff down from the open source EPEL repository, is 2 gig on its own, and then adding more libraries makes that bigger. So size is an issue with all of these. But yeah, there's already folks in the community, the Jupyter folks for IPython and the notebook system, that actually will run a local web-based environment. The Kaggle folks distribute various different for theirs so that you can do the same sorts of things. In fact, they're the ones that keep me into the alias version as opposed to the Docker run version of running it as a kind of a local interpreter. And there's definitely, if you Google for, especially in the data science community, data science containers, there's a lot of people who are talking about publishing them and how we do it and those sorts of things. Any other questions? No? Oh, okay.
What happens when you shave?
Pardon?
What happens when you shave?
What happens when I shave? I don't know. Yeah, it's been, I'm now recognized by it, so I don't think I'm allowed to. So yeah, we'll find out, and hopefully it won't be anything horrible. Cool. Well, great. Thank you very much. I appreciate your time and attention.
Raz, jedna, raz, dva.
Okay, yeah. 1, 2, 1, 2.